Hello guys, how are you today? So today I'll be explaining the physics AMS of term 2 week 12. So let's start with the first question. A pulse in a rope reaches its end, which is free to move up and down a pole. When they say that it is free to move up and down a pole, that means this is a free end. And when we are dealing with reflection, we have two types of ends. Let me kind of make a table. So when we are dealing with reflection, we have two types of ends. We have either a free end or a fixed end. Okay? So for the free ends, what happens is that the image is not inverted, or the pulse will not be inverted. However, in the fixed end, it will be inverted. I believe this is the only difference in between the free end and the fixed end. It's that the free end will have not an inverted image, whereas the fixed end will have an inverted image. Now, here is what they have in common. You will have the same speed, so the speed will stay the same. You will also have same frequency, in addition to same wavelength and same amplitude. So just keep these in mind when dealing with the reflection. You have free end being not inverted, fixed end being inverted, and they share common in that they will have same speed, same frequency, same wavelength, and the same amplitude. So, which of the following will happen to the pulse upon reflection? Because it is a free end, then, first of all, the pulse is not inverted, so this is incorrect. The wavelength will not increase, it will stay the same. However, the frequency of the pulse will remain the same, the speed will not increase, and then finally, the amplitude of the pulse also remains practically the same. We move on to question number 2. Here we are dealing with the reflection of what? Of longitudinal plane waves. So they said that the plane wave strikes a straight reflector. So this is the reflector. Let me just use this over here. So what's gonna happen is that the wave is gonna move towards the reflector, and then because it is a reflector, it will act just like a mirror. So it's gonna reflect the wave. So you will draw the normal and you will reflect the wave. And what's gonna happen is that this angle over here is equal to this angle over here. And so then the waves are gonna be the same, but just like in this direction. Now, what I did was kind of incorrect. Actually, it would look something like this if we are taking into consideration that this angle and this angle is the same. Okay, so then the waves would look something like this. Okay, so always keep in mind, whenever you have a reflector, the waves are gonna be reflected within the same angle of incidence. Okay, so it's just gonna act like a mirror. And keep in mind, this is for the plane waves, which are the longitudinal waves. By longitudinal, I don't mean like the ones that need a medium to propagate in. I mean like these types of waves, they look long. Because we have the circular waves and the plane waves. Okay, so keep in mind, these are the plane waves. So the path of reflection is definitely gonna be this. It's not this because it's not gonna reflect downwards. It's not this because it's not gonna reflect on the other side. And it's not this because it's not gonna go back. So remember, it will strike like this. You need to draw the normal, and then you will just continue the path of reflection. We move on to question number 3. In question number 3, they said, the diagram below shows a ripple tank as seen from above. An oscillator is generating straight waves towards a gap. Now, what you need to know is that mechanical waves, which are the waves that need a medium to propagate through, okay, when they pass through a gap, they will automatically diffract, okay? So they will diffract. So what's gonna happen is that this small space is gonna change the shape of the wave, so then it will come out curved, to come out like this. Okay, this phenomena is called diffraction. So what we need to know is mechanical waves are the waves that need a medium to propagate through. When they pass through a gap, they will automatically diffract. Okay, we go on to question number 4. Actually, wait, let me go to question number 3 and add some extra information. So let us say we are dealing with these waves. Okay, the linear wave, and we had a gap that had a really small opening like this one over here. The diffraction would look like this. It would be curves, almost in the form of a curve. However, if we're dealing also with longitudinal waves, but we have a bigger gap in between the long or the linear waves, okay, only the ends are gonna be curved, so it will come out looking like this. Okay, so keep this in mind when we are solving. Question number 4, 2 pulses of equal amplitude in opposite senses, keep this in mind, opposite senses, are moving towards each other and they meet at a point A. Now, keep in mind they are opposite senses and they have equal amplitude. So what's gonna happen next is when they meet at point A, they will form a straight line for a second, and then they will continue their way with this one going like this and this one going like this. So when they meet at point A, okay, what's gonna happen? It's called deconstructive interference. Interference means the meeting of two waves, whenever two waves meet. So when they are both going in opposite senses, meaning that one is up and one is down and they're both going in opposite directions, then for sure this is called destructive interference, because it's not gonna build a bigger wave, it's gonna either build a smaller wave or it's gonna just like make it a flat line if they have equal amplitude. We move on to question number 5. They said the loudness of a sound depends on the wave amplitude. This you have to have it memorized. Okay, so some other extra information is that the frequency, it depends, or it's directly proportional to the pitch, okay? And this we know that amplitude, it depends on the loudness, or loudness depends on amplitude. That means they're directly proportional. And that the sound intensity I, it is directly proportional to the amplitude squared. So keep these in mind. We move on to question number 6. They said, what happens when pulses in the same sense? What do they mean by pulses in the same sense? That means one pulse is up and then the other pulse is up, but they're moving in opposite directions. So when they meet at this point over here, which we will call A, they will do something called constructive interference. So they will build a wave that is much bigger, and then they will just continue their ways normally. So it is called their amplitudes will add constructively, or in another sense this is called constructive interference. We move on to question number 7. Select the figure that shows the correct interference between two incident pulses. So what do they mean by incident pulses? Means that they will meet. Okay, so let us see what will happen. These, they are in the opposite sense, so it is destructive interference, okay? So they're either gonna make a smaller wave or it will just become 0. So since their amplitudes are both A, they're both the same, they're gonna make a flat line and then they're gonna continue normally. The first one is totally correct. The second one is incorrect because this is constructive interference, which does not happen. The third one is also constructive interference. It doesn't happen. And the fourth one, we never talk about it. No such thing exists. So, yeah, it's the first one. We'll move on to question number 8. Which statement describes circular waves that reach a straight barrier? Now look what's gonna happen. Circular waves that reach a straight barrier. We have circular waves over here. Okay, they will keep on moving until they will reach this barrier over here. This barrier, we will call it B. When they reach this barrier, what's gonna happen is something like a reflection. But look what's gonna happen. Let me draw it in a better sense. Something like a reflection is gonna happen. So new waves are gonna emerge, but they're gonna continue these waves. So if I was to draw another example, so we have the barrier B over here, and we have it like this. Okay, let's say it's like this, the wave. Then the rest of the wave are gonna come back like a reflection, like this. Okay, they are gonna continue it. But what it seems like it, okay, is that there is a point behind the barrier that is causing these waves to form. So what they're trying to say is like it will complete and it will be looking something like this. So what I'm trying to say is what actually is gonna happen is that the waves are gonna reflect from the barrier and they're gonna form like this. Whereas in reality, what it seems like is happening is that there's another center behind the barrier that is causing these waves. So it will undergo reflection, okay, and it will seem that it's coming from a point behind the barrier. Okay, so for sure the laws of reflection, oops, I chose the wrong one, my bad. For sure the laws of reflection are obeyed, okay? Because when you undergo reflection, you have to obey the laws of reflection. So they do undergo reflection, and as we said, the reflected waves seem to come from a point behind the barrier. We move to question number 9. Select the figure that shows diffraction of water through a narrow, keep in mind, a narrow gap. Whenever they say a narrow gap, this means that it's more likely to curve. So definitely, for sure, it's not gonna be a straight line. It's not gonna be like this. It's gonna be curved. It's gonna be way more curved, okay? Because from a narrow gap, let me do it properly. From a narrow gap, it's gonna turn out more curved. However, if you have a wider gap, it's gonna turn out more like a bracket. We'll move on to question number 10. Here you have to keep in mind which graph is the loudest. When they're saying the loudest graph, that means the graph with the highest amplitude. So we're gonna go up and look. This has a small amplitude. This also has a small amplitude. This also has a small amplitude. This has the biggest amplitude. So the answer is B. Amplitude means the height of the wave. Now, which has the highest pitch? Here they're asking for frequency. Let's say all of this is in 1 second. So the one that has the most amount of waves in 1 second, which is D, this has the highest frequency. We move on to question number 11. They told us the diagram below shows some water waves passing through a gap between two stepping stones. Now, what you need to know about the factors that affect diffraction. Okay, there are two main factors that affect diffraction. They are the wavelength and the size or width of the gap. The wavelength, that means the longer it is, the more diffraction will happen. The shorter it is, the less diffraction will happen. If it has a greater width, then a less diffraction will happen. If it has a smaller width, then a greater diffraction is gonna happen. So for sure, it is the width of the gap and the wavelength of the water waves. We move to question number 12. Here I told you to remember that whenever you see frequency, you know that it is directly proportional to the pitch. That means when the frequency changes, then the pitch is gonna change, okay? Which property changes when the amplitude of a sound is increased? Again, as we said, the amplitude is directly proportional to the loudness. So as the amplitude increases, the loudness is gonna increase. Now finally, the sound intensity relative to the amplitude. We know the relation is that the sound intensity is directly proportional to the square of the amplitude. That means if you double the amplitude, so it's like this. If you double the amplitude, then that means it's gonna be like this after you square both of them. So that means you are gonna quadruple the sound intensity. So as you double the amplitude, the sound intensity is gonna quadruple. We move on to question number 13. Two pulses whose shapes are shown on the diagram below move towards each other and meet at point A. Now they need us to find the shape of the pulse at A. What you need to know is that when two waves meet at a point, or there's interference of waves, and they are in the same sense, then they are just gonna be like a combination of the two waves. So the new wave at point A is gonna be a combination of the two waves, and then it will go back to normal. So you have to look for a combination between the two waves. Now the shape of the pulse P after it passes A, we said after it passes the interference point where they will create this new wave, they're gonna go back as normal. So definitely you're gonna choose something that is normal for which has a similar shape to the wave of P. So you're gonna take this one. Now they don't look the same because these are kind of like squished, so pay attention, okay? Now, this phenomenon described above, when two waves, they have an interference and they build up, so it's a combination of the waves, this is called constructive interference. We move on to question number 14. A sound wave train is sent towards a concrete wall at time is equal to 0 seconds. The wave train reaches the wall at 0.2 seconds and reflects off it. So look what happens. This is our wall. We have a sound wave train, which looks like this. It's sent towards the wall. Okay? So here it's 0 seconds, here it's 0.2 seconds. And then it will bounce off the wall, meaning it will reflect off of it. So what's gonna happen is that it is gonna reflect off of it like this. Or to be more specific, like this. So it will be something similar to the one before. But because it's reflecting off the wall, so let me just like draw it in another example so that it's more understandable. Okay, so let us say this is our wall over here, okay? Here we have our wave that will look something like this. Here 0 seconds, here 0.2 seconds, okay? They told us that it will reflect off of it. Whenever we say it will reflect off of it, from the place of reflection, so it will reflect off of the wall. From the place of reflection, what is gonna happen? A reflection will happen, but this reflection, so because a reflection is gonna happen when we are representing it on the graph, okay, it's gonna be almost like an image on the other side. So it's gonna look like this and like this. So it's literally gonna be like the image, like 0.2 is the mirror over here, and from here you will copy it like an image. Okay, so this is all that I have to say for this. So select the correct diagram that describes the displacement time graph for the reflected wave train. We said that when we are dealing with the reflection of a sound wave, we will take the point at where it reaches the boundary of reflection, which is over here, and it will act like a mirror. This boundary will act like a mirror, and it will copy the wave on the other side. So it will look something like this. Now, assume that the sound wave partly refracts into the wall, because we know, just like light, okay? Let's say again, this was the graph. This is our boundary B, okay? This is the sound wave, and then it will come back like this. It will literally reflect, okay? But there is a little bit of refraction that happens. Okay, it's just like the light. This is the light, this is the normal. Light comes here, reflects here, and there's a little bit of reflection. It's the same case as the same scenario as the light. So upon a refraction, what you need to know is that the frequency and the period, they stay the same, but everything else will decrease. This is if you are going from a less dense medium to a denser medium. For example, from air to water, okay, they will decrease. However, if you're going from water to air, they will increase. So remember, these, whatever is not frequency and period, when you are going from less dense to more dense, they are gonna decrease. However, when you are going from more dense to less dense, they are gonna increase. So keep this in mind. We go to question number 15. In question number 15, they said a stone is thrown into a lake. After 2.6 seconds of this event, a photo of the lake surface is taken and shown in the diagram below. The dark fringes represent the peaks of the water waves. The smallest graduation of the grid represents 20 centimeters. Okay, all you need to know is that they're saying each block is 20 centimeters. They said the water wave can be classified as what? Because it needs a medium to propagate. Whenever you see medium to propagate, this means a mechanical wave, okay? And the water can be classified as, because displacement of particles is perpendicular to the propagation direction, this is transverse. Whenever you see perpendicular to propagation direction, this is gonna be transverse. Now, they told us in part B, the wavelength of the wave to 1 decimal place. To find the wavelength of the wave, we will take the distance from crest to crest. So you don't consider this, okay? And then you start counting. You will have 1, 2, 3, 4. So the distance, it is 4 blocks. And we said that each block is 20 centimeters. That means 4 blocks is 4 times 20 centimeters, which is 80 centimeters. They need it in meters. So you will divide by 100 and you will get 0.8 meters. Now, for the second part, this is very tricky, so please pay attention. They said the speed of the wave to 1 decimal place. To find the speed of a wave, we know that it's gonna be the wavelength over the time. But we don't have the time of one wavelength. We actually have the time of the full wavelength. Okay, but the full wavelength will not be from crest to crest anymore. It will be from the center, the starting point, to the final point, okay? You do not consider the point of the center. So now you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now this is all of it, 16 blocks. So in total, it's gonna be 16 times 20, which is 320 centimeters. Change it to meters, this is gonna be 3.2 meters. Now, this is what we found, the total wavelength, and we have the total time it takes from the center to the final point of the wavelength. So the total wavelength, which is 3.2 meter, over the time, which is 2.6 seconds, you will get an answer, which is 1.23 meters per second. 1.23. Now, the frequency of the wave to 1 decimal place. You should know the equation is frequency is equal to what? It's equal to the wavelength divided by, it's not the wavelength, it's the speed, the velocity v, divided by the wavelength lambda. So we have the speed it is 1.23 meter per second. We will divide it by the wavelength, which is 0.8. So on your calculator, you will do 1.23 divided by 0.8, and you will get an answer which is approximately 1.54 hertz. And just like this, we found what? We found the frequency. We move on to question number 16. Consider a light passing through a small slit projected on a screen. Small slit, this is an obstacle. The light pattern obtained on the screen is shown below. So what you need to know is that the phenomenon being observed, it is diffraction. Why? Because diffraction, it is the spreading of waves around obstacles. And because there is a small split through the screen, then this is the spreading of waves, so this is diffraction. Now, what phenomenon explains the fact that several additional light fringes are seen on the left and right? So they're saying, why are there waves here and here? And why is there one big wave over here? This is very simply constructive interference. So it's like this. You have a small wave over here, small wave over here. They're coming towards each other. They will meet at point A. They will create a bigger wave, and then they will continue back their own paths. This is just very simply constructive interference. Now finally we move on to question number 17. They said the type of radiation whose wavelength is stronger than that of visible light but shorter, not stronger, sorry, longer than that of visible light but shorter than microwave radiation is. You have to memorize radio wave, microwave, infrared wave, visible light, then we have ultraviolet, then we have X-rays and gamma rays. Keep these in mind. So they said which wavelength is longer than that of the visible light but shorter than the microwave. What you need to know is how the wavelengths increase are like this. So this is long, this is longer, this is shorter, this is shorter, and they keep on getting shorter. So they told us which one has a wavelength longer than visible light, so anything here is longer than visible light, but shorter than microwave, but it has to be shorter than microwave. So you're only left with this option, which is the infrared radiation. The type of radiation identified in A, which is infrared radiation, passes from air into water, so from a less dense to a more dense substance. This is refraction. Remember, we said refraction from less dense to more dense. Frequency and period will stay the same, but the speed and the wavelength, in this case, they are gonna decrease because it's going from less dense to more dense. So remains the same, decreases and decreases. Let us submit. Hopefully we don't have any mistakes. And thank God we don't have any mistakes. Thank you guys for watching. I hope you enjoyed and have a wonderful day.